Welcome back. Today we'll be talking about z-scores and standardization. And before you ask, yes, this is the same standardization as a standardized test, except that we'll see this kind of standardization has nothing to do with the drudgery of the tests themselves, and everything to do with making the scores more interpretable. Z-scores are a special way of transforming variables with different means and different dispersions so that individual values can be compared to typical values more easily. You might wonder why transforming your data is good if we work so hard to get valid and reliable measures in the first place. The answer is that many transformations don't get rid of data. Often they don't even change the shape of the distribution notably. What they do accomplish, however, is to move from raw units that can vary as much as the number of space launches, per capita consumption of cheese, and annual gross arcades revenue, to a scale where the values mean much the same thing regardless of the original units being considered. Now, box plots might help a visual thinker understand this. So I've got some box plots over here. When I explained the purpose of box plots, I gave you a caution not to combine variables with extremely different scales in the same box plot, because those with larger ranges or higher maximums can compact and obscure useful information about the other distributions. So that's the case we have up here, although this isn't very extreme. Often it could be way up here for the other one, and so these ones would all be squished down so you couldn't hardly tell them apart at all just by looking, even though you can tell they're notably different. A box plot of standardized variables with each value converted to a z-score instead has all the means centered at 0. You see these are the same 5 variables. I've centered the means at 0 and a range of around -3 to +3. The size and position of the box, whether one end is longer than the other, and the whiskers can become highly instructive compared to other plots. So in here we can see, for example, what we couldn't see about these last two plots here. They looked almost exactly the same in the top box plot, but once we standardize, we can see this one has much higher variability. It's got a much wider range within the quartiles. So, I'll assume for the moment that I've successfully convinced you that z-scores could be useful, or at least convinced some of you. So how do you get them? Well, the process is relatively simple once you know how to calculate means and standard deviation. It's a two-step process. First, you subtract the mean from the value. So the x value minus mu, or the mean. This is called mean centering, because it converts the mean to be equal to 0. So scores below 0 are below the mean. Anything above 0 is above the mean. The ranges, though, can still commonly differ by a factor of 5, 10, or more if the ranges are wider or narrower around the mean for a specific variable. So we need a second step, which is we divide the mean-centered value by the standard deviation of the variable. That's a sigma for standard deviation. What that does is it makes it so that the same interval from 0 to 1 means the same thing on all of these. It means one standard deviation difference. So we can look across all of these with different ranges, different scales, and see which ones have higher variability, which ones we still have the same outliers, you notice, but now we can tell which ones are less precisely measured, you could say. Notice you can only standardize an interval or an interval-like ordinal variable. A categorical variable doesn't have a standard deviation, so you can't standardize it. Now this second step then accomplishes the goal of making values comparable across variables with different raw scales, or sometimes even the same raw scale but with different levels of variability. Now, if we were to repeat this for every value in a data set, so if we say were to add xi, mu x, sigma x, so now, right, we actually have not a sum. We have all this I equals 1 to n, essentially. So each case, from the first case to the size of the sample, we would calculate the z-score by repeating this. The value minus the mean means the same for all of them, divided by the standard deviation, which is the same for all of them. The result of that is a z-standardized, or commonly just called a standardized variable. That is, every value would be equal to the number of standard deviations the raw score was above or below the mean, which is what we see here in this bottom box plot. This is z-standardized. This becomes even more important later because, at least for a normally distributed variable, the proportion of cases within a number of standard deviations of the mean is well known. So, for example, slightly more than 95% of cases will fall within 2 standard deviations above or below the mean. And the converse is also true. If the standardized value of a case is outside that range, we know at a glance that it's in the most extreme 5% of cases or less. That's about it for z-scores, but there are a couple side notes that can be important to remember. One is that variables can be transformed to have other means and standard deviations than 0 and 1. The most common example of this is standardized tests, like IQ tests, many of which are scaled to have a mean score of 100 and a standard deviation of 15 in the population. So if these were IQ tests and other tests standardized to that same scale, this would be 100, this would be 15, this would be 115, this would be 85, and so on. By doing this, they can keep the same relative distribution of scores between years, even if people do better or worse on average, and between slightly different scales that measure similar things, and simplify interpretation without having to tell people, for example, that they have a negative IQ if they were to score 85 on this, which would be -1. To standardize to other values than 0 and 1, just do the same thing but subtract the difference between the mean and the target value, or the mean and the target mean. So in this case, you would subtract out the difference between the actual mean and 100, and then divide by the standard deviation and multiply by the target standard deviation. That last step makes it so that these distances are correct. So one more side note. Because standardized scores depend on the mean and variance, a small number of extreme values or very unrepresentative cases can bias the mean up or down and will greatly increase the standard deviation. So the implication of that for z-scores is that that can make them fall within a much narrower effective range. Because the standard deviation is higher, the z-scores of the other non-outliers are compacted down. So the moral of this story, though it may start to sound like a broken record the longer you're in this class and watching these videos, is to know your data and be aware of the potential problems before you analyze it so you can factor them in when you're thinking about it. That's all for today. Z-scores and standardization sound difficult, but actually, as you can see, they're fairly quick, fairly painless to perform once you can do means and standard deviations, and they can accomplish some important goals. See you next time.